Okay, thank you for coming. I hope that you learn something about time series analysis. I think I've ever since I was a graduate student, in fact before I was a graduate student, I thought time series analysis looked like a really interesting area, and I guess I've worked in it. I've worked in it ever since PhD, and ever since with a slight dalliance into criminology, but primarily it's been time series analysis with an economics focus. So there will be a little bit of a bias, if you like, towards economics, because and the economic type applications of time series, just because that's what I'm familiar with. That's what I know about, basically. But there are much more. Okay, so what is time series analysis? Well, a time series is just a set of data observed over time. It could be anything. It doesn't have to be economics. It's just a set of data. So there's stock market returns in finance. If you're interested in investing in the stock market, you might be tracking the daily financial returns. Well, you look at each day's returns over time. You're at least informally doing time series analysis. You might think about the monthly rainfall patterns in Manchester, which would be an application of seasonality. If you're particularly interested in the patterns over the year in rainfall, that would be a time series analysis of the seasonal pattern, how it changes over the months of the year. Something I did do a little bit of work on, as I say, my dalliance into criminology. I did do a little bit, was mainly cross-section, but I did do some time series analysis as well. I couldn't resist it. And patterns in the number of recorded property crimes on an annual basis of the last about 50 years. There's aspects in terms of cycles, periods when they go up, periods when they might decline. And so there's cycles of activity. And then there's things like weekly online sales by Amazon. Well, I'll bet that has a seasonal pattern with a peak at Christmas, but it also has a trend because it's gone up hugely over time. So there's various characteristics. Any of those things are time series. And time series analysis is simply in a nutshell, is the analysis of that. But it's in a sense, it's more particular than that. It's the statistical or econometric, if you like, depending on which perspective you come from, the statistical or econometric models that are used to represent the characteristics of these data. So putting these data into a statistical context and then using the results. Why do you want to do that? Well, there's lots of reasons why people do it. There's understanding changing world temperature patterns. Has global warming? Has there been global warming? Well, you need to analyse what the temperature patterns are now compared to 2050 or whatever your timescale is ago. So you need to understand that where there has been a change, and that needs a statistical framework to do it. There's a big literature that I know very little about, but I've glanced at a few papers and time series on predicting river flows, how river flows change over time. It's partly seasonality, the patterns of river flow, but it is they use quite complicated time series analysis techniques in the river flow analysis. Something I'm much more familiar with, the last two, forecasting future stock market returns. Well, you can try and do it, and many people do try and do it, whether they do it informally, chartist approaches or hunches or whatever, information gleaned from financial press. But but within firms that specialise in that, there's a huge industry in time series analysis. Actually, they pay people who do this sort of analysis huge amount of money, the econometricians or finance people who do this find the time series analysis in that context, because they're interested in, if they can forecast future stock market returns, they can sell their services to people on the basis of the returns they've made. So there's a big industry in forecasting future stock market returns, whether it's informally or formally. And it's the fundamental technique used in, or one of the, perhaps not the fundamental technique, one of the fundamental techniques used in macroeconomics to evaluate macroeconomic policies and the implications of macroeconomic policies. So the Bank of England has a big team that will be doing time series analysis of one type or another, the Treasury, International Monetary Fund, all the important international economic organisations will have teams of people that are doing time series analysis, analysing data over time, whether it's economic growth, whether it's inflation, or whatever it is, all the patterns in that. Okay, so here's an example that I put on the outline. If you looked at the outline on the website, this is from the Bank of England. It's taken from the Bank of England website, where they very conveniently give you all the slides for all these things. I guess so that we can all do talks and talk about what the Bank of England's doing. So with thanks to the Bank of England, this is their August. I had hoped to get yesterday. They did the November forecast. This is the August forecast produced. They produce a forecast every 3 months within the Bank of England, and they publish lots of pictures. But this is the picture about annual inflation from their inflation report from August, and it gives you some record of the recent past of how annual inflation, so inflation in any quarter, that's a quarterly model, in any quarter, let's say the first quarter of 2010 compared to a year earlier. So it's inflation, percentage inflation over the year from one quarter of a year to the corresponding quarter of the next year. So this is the annual inflation in the consumer price index, the current main series that the Bank of England looks at for the recent past. Nice big peak here, went down again, and as we know, it's been coming up again recently. And this nice thing on the right is what the bank produces as their forecast of inflation. And their forecast of inflation is in the central most red bit, perhaps the colour. You can see there are different shades of red, but it perhaps doesn't come out quite as vividly as it does when you look at a picture on the web. But the central forecast is in the middle. So if you like, their best bet lies here in the middle in this darkest part. And as you go further out in either direction, they think there's a less probability, a lower probability. And they say they think there's a 90% probability of falling within the outer and the upper and lower bands. So it's like a confidence interval for a forecast. And so the upper and lower bands would give you a 90% confidence from the Bank of England that if they didn't change interest rates, this is based on if Bank of England did not change interest rates, this is what they forecast would happen to UK inflation over the next couple of years. So they think inflation is going to come down, but they think there's a non-trivial probability, not high, but a non-trivial probability if you go back up to something like the getting on for 5% as it was a couple of years ago. So that's an application of time series. Time series are used to produce this forecast. It's actually, I do a lot of things actually in the bank to get to that, so it's not just as simple. I don't want to give you the impression that it's something someone does in half an hour on a computer. That's certainly not the case. There's a lot of analysis and discussion goes into these, but you can see it as an output from the time series analysis. And as one of the characteristics that the bank has been very good in promoting is this idea of probabilities and ranges, rather than just saying our best guess is that inflation is going to come back to 2% in 2000 and middle of 2011. They're saying that, well, we think they're giving a range for their forecast with a probability attached to that, and that's one of the things the bank has been very good at. Anyway, in effect, I've talked about the next slide implicitly in my earlier discussion. So time series patterns are often divided into trend or change of the level, seasonality over the year, and cycles such as recessions, expansions. And that's a useful way to think about the features to be presented in a time series. There could be other features, but often those are the key features. And the old literature of time series analysis back I guess in the 60s used to revolve around those things, but now they're captured more. These aren't thought as necessarily separate anymore. Whereas back in the 1960s, people would think about, well, we use a linear trend to take the trend, and then how do we capture them? They thought about these as quite separate entities, whereas now it's more thought about as a holistic, if you like, characterization. But it's a useful way to think of the characteristics you want to capture. You might guess I have a particular interest in inflation. In recent years, last 2 or 3 years, I've done quite a lot of interest in it, a lot of work myself on inflation. So this is actually a different representation. This is again UK consumer price index inflation, but this is on a month-by-month basis. What I looked at before in the previous slide, a couple of slides ago, just to hear this history, this was annual inflation. It's one point of time compared to a year earlier, percentage increase literally over a year. Mm-hmm. Whereas this is the month by month increase in inflation. So prices this month on a monthly basis compared to a month earlier. It's scaled up to give you a percentage rate that would look like an annual inflation rate. So it's scaled to be on the same, but it's actually month by month rather than over a year. So it has quite a, you can see the way you choose to represent even the same data in a time series context can have an entirely different impression of what there is in the characteristics of the series. If you go to this level of the monthly inflation rate, the main characteristic is seasonality. Now this is since 1993. You can't see anything obvious, at least, in terms of whether the level of inflation has changed, which you could see in the previous graph. What strikes you here is the pattern over the year. And in what it says here, that the main patterns are induced in July and January. There are big dips because of, your thoughts? Why? Sales, absolutely, because of sales in shops. Inflation is actually negative. You just look at January and July compared to the previous month, inflation is negative. It's negative, no surprise. So that is the consistent pattern. And the increase is often, not always, but typically the increase is April. In the UK, why is the increase in April? Pardon? Financial year, yeah, because at least, not quite so true now, but because the budget used to always be in April, but traditionally the budget's been in April, and many tax rises came into effect at the end of the month or during April. So the consumer price index, when measured in April, has a peak in April because of the changes in taxes. So you can explain why that pattern is there, but as I said, it gives you an entirely different impression of what there is to think about in terms of the patterns. Whether you choose to look at month-by-month inflation, you get something similar if you did quarter-by-quarter inflation, or whether you take inflation compared to a year earlier, which gives you a much smoother picture. So it depends on your purpose, ultimately, which is the right graph to use. And the one interesting thing about the recent past here is this, there's actually here a sequence of, I think it's 3 or 4 months of negative inflation here, and that's the hit of the most recent recession. Okay, so the first issue is what patterns are there in any series, what time series patterns over time, what patterns are there to be explored and thought about and ultimately represented in a statistical model. You can use a visual approach, and my students get fed up sometimes with me saying, where's the graph, let's look at the graph. So I don't think you can ever, in a time series context, you can never do away with looking at graphs. They're indispensable to get a handle on what's going on, as we've seen in a couple of examples. Or you can use a statistical approach, or better, and almost always to be recommended, is to use both the graphs.
Can I be pedantic?
Yeah, Chris, go ahead.
Can I say I don't think there's a distinction between graphical approaches and summary statistics. My view is that a graph is a summary statistic.
Okay, you can view a graph as a summary statistic. Okay, fair enough. It's just what you call a summary statistic, isn't it?
My point is I agree that graphs are invaluable.
Okay. In this time series context, what's the primary descriptive statistical tool? It's correlations. And we know correlations, you talk about, assuming you've all done a little bit of statistics somewhere on the way, you talk about the correlation between height and weight, or whatever two variables you're thinking about. You think about how simple way do I, in a descriptive level, talk about the strength of the relationship between these variables. You look at a correlation as a first snap of a summary statistic. Well, in time series, we talk about correlations. But we only have, well, at least in this context I'm currently talking about, we only have one series we're looking at. Inflation, or river flows, or temperature, or whatever it is we're interested in. So we talk about the correlations of the variable, whatever variable we're interested in, with itself. So known as autocorrelations. So how do we do that? Well, let's say, keeping the inflation context, let's say we're thinking of monthly inflation over some period, let's say January 1988 to October 2010, whatever. And we call those monthly observations of inflation, first one Y1 in time, the second one Y2. There's a natural, just to emphasise, in a time series there's a natural ordering of the data. That's often not true in a cross-section, but in a time series, time itself gives you that natural ordering of the data. So you don't have to worry about the ordering. It's a natural because the time gives you that natural ordering of the data. So conventionally, the first observation we happen to work with is just observation number 1. It might be October 1988 or January 1953 or whatever our time span is. And then the second one is Y2, etc. So we have a sequence of observations over time, of whatever variable, rainfall, inflation, or whatever we're looking at. And when we've got those observations, the autocorrelations, or in this case sample autocorrelations, are the correlations of each value of y with some past value. So how closely correlated is inflation in adjacent months? One month following the next, or how, and they're the autocorrelations. So let's have here's the UK inflation again, monthly inflation again, and here's it might be easier to talk about what the graph tells us. So here's a graph, the autocorrelation. So the first one is a correlation between each value of inflation and the value in the preceding month. So we've got, let's say, 200 or whatever it is observations in our series. So we've got, if you think of pairs of each value of y and the value in the preceding month, think of y now and think of y in the preceding month, call that x. So you've got another variable. So whatever inflation was last month, call that your x variable, and then you take the correlation between those two values, inflation now and inflation last month, for over the 200 or whatever it is observations, and that gives you a sample autocorrelation, and that's a sample autocorrelation at lag 1, with y and the preceding month, so that y and y minus 1. So that's autocorrelation at lag 1. Similarly for lag 2, you do the same thing. So you've got your inflation and your inflation rate 2 months earlier. So that now becomes, inflation now is your y still, inflation 2 months earlier is your x variable, and you take the correlation, sample correlation between those. And that's the autocorrelation at lag 2, it's corresponding 3, 4, etc. You can see you can do this as far back as you want to in terms of how correlated is the value now with so far earlier. And this for this UK monthly inflation, the first peak here is at 12, so inflation is highly correlated, about correlation of 0.71. Inflation in any single month by month, compared to same month a year earlier. So January sales occur in January. So what happened in January now is very similar to what happened in January a year ago. And and that's even at 24, still pretty strong. It's hardly gone down. And 36, again, it's only very slightly declined. So inflation is quite highly correlated with a year ago, 2 years ago, 3 years ago, etc. in the corresponding month. The other peaks here are 6 months. So the correlation here, slightly less, around 0.4, is 6 months, and that's largely driven by the January and July sales, in fact, because the sale periods are quite like each other, and that's why you get the correlation not as strong, but quite as strong, but that's the correlation at 6 months is driven mainly by those. And similarly, 18th and 30 months by the same logic. And in this case, this correlation pattern, particularly the peaks at 12 months apart, confirms that the main characteristic, in terms of a time series characteristic, the main characteristic is the seasonality, with every year to 12 months. Here's another example, which is a bit less obvious. This is real output growth, percentage real output growth for the UK economy. It's a so-called gross value added measure, but don't worry about that. It's a real output, national output growth for the economy. It's available quarterly and it's seasonally adjusted, so they're trying to get rid of the seasonal pattern. We won't talk about how they do it, pros and cons of that, but the main output measures that are used when people talk about output growth, GDP growth or whatever in the economy, they try to take out seasonal effects. And that's the graph of by quarter from 1960 until the second quarter, I think it is, of this year, is the actual time series graph over time of the patterns in output growth. And you can see the recent recession again, the big drop in output. Here's the recession, smaller recession back here in the early 90s, and then some blips around the 1970s, particularly around 1974 and around the early 80s. with the recessions of those periods. But it's quite erratic, it's quite different. It's harder to see a pattern if you just look at graph that. If you looked at the output series itself, which I didn't include a graph of, but if you looked at the output series itself, it's virtually always going up. The level of output of the economy is virtually always increasing, except of course for these blips where there's recession periods. So output growth, by looking at the percentage change, takes away that trend. And the principal time series characteristics here, is there anybody, it looks pretty erratic here, and one of the things is output growth substantially became more, less volatile, moderated. The volatility became much more steady from the period of around about the mid-1980s. And that to me is the main characteristic that comes out here, at least initially from the graph, is that it's not so much something like seasonal pattern, it's actually that something seems to have changed. It's much less variable now than it used to be, with the exception, of course, of the recent recession. But even then, it looks sort of quite steady. You don't have this very erratic up and down pattern now.
Do you know why that is?
Well, I would say that there's in economics there's still a debate actually. This is characteristic not just of the UK but of many developed economies with similar patterns. And there's still a debate that hasn't completely been resolved about whether it's because of better economic policies, which of course the economists would like to claim, or whether it's good luck. There's this literature, good policies or good luck. And there's probably some elements of both, to be honest, because I think economic policy has improved a lot, but it's not crystal clear. Even it is been quite an active area of debate actually about why that's happened. So if we did the same graph and did the autocorrelations, just check the autocorrelations of output growth with its own past, 1 quarter, 2 quarters, 3 quarters, we get much less strength. It's about 0.18 or so here for the first 3 quarters, but it's nothing like the strong. There's no strong correlation over that period of output growth with preceding output growth. So it's relatively low. Something perhaps at the preceding 3 quarters, like the autocorrelations 1, 2 and 3 lag, so this 2 quarters earlier and 3 quarters earlier. But as I say, not like the 0.7 or the very strong correlations that we saw in the previous graph. One of the interesting things I discovered actually when I was preparing these slides, that I thought, volatility declined around about 1985. What's happened to the correlations? So I did the graph of I did the autocorrelations since 1985, and I hadn't actually realised it. I've learned something, that they changed so dramatically. So over the whole period, from 1960 to 2010, there's not very much. And if you look from 1960 to the mid-1980s, there's not very much. But if you look from the mid-1980s to now, basically, there's quite strong correlation, about 0.65 or something like that here, between adjacent quarters. So the correlations of growth, surprised to find out, are much stronger since 1985. And that actually is good news for a time series analyst, because if there's a regular pattern like that, there's quite strong correlation, then there's some possibility of forecasting. If you can detect a time series pattern, then intuitively you can project that pattern to the future as a forecast of what's going to happen to GDP growth. So that takes us nicely to talking about the sort of statistical models that are used in this context. This is not just about looking at graphs or summary statistics, but that's sort of a preliminary to a lot of them. How do we pin that down in terms of a statistical model? So the simplest statistical model has this form, which is like a bivariate regression. A bivariate regression would have a dependent variable y, it would have an explanatory variable x. So here, playing the role of your explanatory variable x in your bivariate regression is actually the own past value of y. So inflation, GDP growth is better because there's a pattern between adjacent quarters. GDP growth now is regressed on GDP growth in the preceding quarter. So you just take that as you've got the values of that, so you can treat it as a separate variable in a regression sense, and regress the current over all the 100 or whatever it is observations you've got, take all the current values of y, treat that as the series of output growth, that is your dependent variable. Take the series of output growth in the previous quarter, line those up now as the x variable corresponding to y, and do a regression of output growth now and output growth in the previous quarter. And if it's a first order autoregressive model, what you're left with is just random, purely random, no pattern of any type in it. So it's a regression of y on its own path, hence the term referred to as an autoregressive model, regression in itself. And in this case, it's an autoregression of lag 1, because we're just going back one period, 1 quarter, or 1 year if you had annual data. So if we applied that simple regression framework, if you like, to the output growth, and I did two, I took the quarterly data that we saw in a graph a little while back, between 1960 and the end of 1984, and in that regression, okay, I've got a constant. This is the t ratio, so that's highly significant. The 5% level of significance, the critical value is something like 1.96. So that would be, this is the t ratio, so that's highly significant, the constant. Just means on average there's growth, basically. And this is the first order autoregressive coefficient, 0.009, with the t ratio being 0.08, nothing. There's no relationship, that would say, between the value now and the value in the preceding quarter. The R-squared measure is 0. And the residual standard deviation, the standard deviation of what's left, is 1.18. From 1985 to the same exercise, the first quarter of 1985 to the second quarter of 2010, okay, I've got a constant, but the first order autoregressive coefficient is now 0.664, t ratio of 8.86, that's highly significant. So again, in a statistical model sense, showing us that there's a big difference between the pre-1985 and the post-1985, with an R-squared of 0.440, and a residual standard deviation of what's left, of 0.5, which shows much, well, less than half of what it previously was, so showing the volatility's declined substantially. There's a whole literature in time series now about testing, whether there's significant difference. The so-called literature on structural breaks been around for a little while, but particularly popular in econometrics at the moment. So the regression model you can use in the sort of way you can think about as two variables. There are some theoretical issues here that I won't go into, that all the assumptions you make about a regression model don't hold true in finite samples, so all the results are asymptotic or large samples. In principle, they only apply if you have a lot of observations and large sample results. But in practice, in practical terms, you can use the techniques of regression to actually do the estimation. Any regression package would be able to do that simple estimation. And you can then use it for forecasting. So how would you use that for forecasting? So if we had that, if I put it into just an equation like this, so that's my regression model I've just shown for the period from 1985, as written down as regression with y, previous y, and what's left, the residual. How would I then use the forecast? Well, it's naively, it's just what you think you ought to do, logically do, is what is, under certain assumptions, optimal in this context. So in other words, if you were forecasting the third quarter growth this year, you know the second quarter growth, so you just plug the second quarter growth in as the yt minus 1, basically into that, take this part of the equation. If this is purely random, you can't forecast something in the future that's purely random and means 0, so you can't do anything about forecasting that. So your best forecast, optimal forecast, lots of assumptions and skimming over lots of things, but this gives you your optimal forecast. So that would say the forecast for the third quarter of 2010 were given by using the second quarter, and if I want to forecast further ahead, the fourth quarter, I then use that third quarter forecast, plug that in, and produce a forecast for the fourth quarter, etc. And I could continue that as far ahead as I wanted to go to produce forecasts. So you might say, okay, that's fine. I could have produced a forecast for you for the third quarter of 2010, but I thought, okay, let's do something slightly different. Let's try and see how well it would have done if I'd used that simple mechanism to forecast the recent past. So if I took the data up until the end of 2008 You just use the data up to the end of 2008 and say, how will it, would it then have forecast 2009 and 2010? Okay, that's the idea. Just use the data up to that point, estimate my regression model, and then use that simple simple technique to forecast what 2009 and 2010. And in fact, it does. I was amazed. It does very well. So these are the forecasts that that are produced out of that simple running it ahead, 1 quarter, 2 quarters, 3 quarters, 4 quarters, and these are the actuals. And in fact, as these things go, that's pretty good. Forecast rather well. So I thought that's fantastic, but I was pretty sure that wasn't that actually was in some sense by luck. So it's forecast recovery from the recession, which is basically what's going on this period. We start from the recession in 2008 and we're forecasting. We know it recovers and it's forecasting that, tracking that recovery. Even though all the forecasts are from the end of 2008, I haven't used any data beyond that. I've just pushed those forecasts forward and knew that wouldn't look so good if I went back earlier. So if I do the same exercise and stop at the end of 2007 and then forecast the onset of the recession, my forecast has been a period of quite steady growth up until the end of 2007. There's been, so the 2000s were a good, up until the recession hit, the 2000s were a good period. So my forecast just says that good period is going to continue, basically. So the forecast says growth is going to remain steady at around 0.6 or so % a quarter, which is basically the average rate of growth in the UK. Actual, if the recession hits, and of course there's nothing in my simple model that could forecast a recession. So it does rather well in a period of steady growth. It does appallingly when something changes, like the recessions, but nothing to hang with the onset of the recession or the forecast the onset of the recession. And it does touch on my next slide actually, because what I just pulled out of a hat actually, well, yeah, largely pulled out of a hat and said, let's take a first order autoregressive process. What we're looking at, even in this univariate context, we're trying to match the values of our series with what's happened in the past. And I just use one lag. And so there's a big a huge part of time series analysis about how you specify the model. You can generalize the first order case to having 2 lags, 3 lags, 4 lags, etc., to having more lags. And that may help to capture some of the features, seasonality, business cycles, etc. But you need to decide how to use, how many lags to use. And there's a literature on that. It's a large topic on how you would choose the appropriate model to, even if you say it's a linear or regressive model, how you choose. But basically it's either hypothesis tests or there are other, not necessarily hypothesis tests, there are other data-based, looking at the data-based procedures to decide whether it's 2 lags, 5 lags, or whatever. It's also the question of whether the linear specification, maybe it's not linear, maybe there's something non-linear. It's not necessarily the simple linear relationship, maybe non-linear. There's a whole area of time series analysis that talks about non-linearities and what types of non-linear models might be suitable in different contexts. It's non-trivial in practice, non-linear modelling, but doable. There's a large literature, and ultimately there's also diagnostic checks, so diagnostic tests that are available to check that your model residuals are random over time. The idea of a time series model is that all the pattern is captured in this part, and what's left in the U is just purely random. There's no pattern left in it, with all the randoms, all the systematic part is explained, and what you're left with is just a non-systematic random component. Let me just spend 2 minutes before Chris stops me to talk about multivariate models. So all of that was a single series in isolation. Model a single series in isolation is not always useful. Economics, it does have uses, but it's often more useful to look at relationships between variables. And then you can generalize. You can generalize the models so that rather than y depending on its own past, yt minus 1, it may also depend on some other variable. And similarly, this variable x I've called here may depend not only on its own past, but may depend on the past of y. So you can, even in this dynamic context, you can get into quite complex interactions between 2 or 3 or however many variables you're looking at. So you can have more variables, you can have longer lags than one, and again, in this context, is model specification, deciding how many lags and indeed how many variables you need to look at together to capture the important interactions is big questions in this literature.
Please don't advocate gender specific.
I wasn't going to even mention gender specific, Chris. This framework is known as a vector autoregressive model. So it's autoregressive, but it depends on something else, so vector autoregressive. Coming from a terminology in statistics, but that's not. Let me just give you a little graph before I stop, rather than going into details, etc. This is how in particular, how macroeconomists use this. Macroeconomists use these vector autoregressive models a huge amount in their time series work. And these are graphs from a paper of my own with a co-author, which we were looking at the interactions between the US and the euro area economies, and one of the aspects we were looking at was how interest rate changes in the US affect interest rates in the euro area and vice versa. And here, the dots are a confidence band. That's about 66% one standard error confidence band, so about 66% between the two, confidence between the two limits. If interest rates in the US change, in particular if they increase, what happens working through the interactions between these 7 variables, so there's inflation rates, there's exchange rate, there's output growth in there. There's quite a big effect on the interest rate of the US, interest rate change in the US has quite a big effect in the same direction in the euro area. So euro area interest rate have to respond basically if the US interest. It might take a little while, but they respond. And perhaps it's not surprising, but our framework tells us, which is that's a sophisticated version of a vector autoregressive model, that the opposite isn't true. If the euro area changes its interest rates, the US basically reaction is very small, tiny. We look at the different scales here, and it's not significant in terms of the confidence band always includes 0. So you can use these models to look, macroeconomists use them all the time, to look at these interactions between variables to try and look at where the important, how long effects between one variable and another, etc. take in this framework. Chris.
What's the actual solid line? Is that the actual interest?
That's the impulse response function.
Right.
So it's no, it's not the actual. It's the reaction to a shock. But
Okay.
yeah. So it's the estimated effect of an interest rate change from the US on the euro area. Okay, I think I've said that, and I've said about the vector autoregressive models being widely used in economic policy analysis, especially in central banks. So central banks, one of the core things they look at in terms of their time series models will be a vector autoregressive model. So they won't be looking at inflation in isolation of anything else. They'll be looking at inflation in relation to interest rates, output growth. They might have other countries' effects in there as well. Okay, and I think my final slide just says, talks about the time series analysis. We're interested in focusing on capturing patterns over time. The intuition, hopefully I've been able to give you a little bit of the intuition, is I think fairly straightforward and what we're trying to do in it, but of course the implementation is by no means as simple as the intuition here, and some of the theory of time series analysis is very complex, so I don't want to make it seem, and it does have its own issues compared to general statistical theory, because this pattern of time does bring out particular issues, so it does have its own time series analysis theory strand. But they do have wide variety of applications, and as I say, I've focused largely on economics because that's what I know about. That's what I feel comfortable with.
Okay, thanks, Denise.